Actually set me up just perfectly there because my name is Michelle Thaller, and what I'm going to talk to you a bit today is our Planetary Defense program at NASA. So all of these things, like the dinosaurs didn't have a space program to defend against, NASA is now taking the first steps so that we do have a way of actually defending the Earth. It's an interesting term, planetary defense. A lot of people have heard of planetary protection, and that's another thing that NASA does that actually limits contamination, both things coming back to the Earth and things that we bring to other worlds. But we also have an office of planetary defense, and that involves mainly asteroids and comets. So I wanted to start with something just pure fun, and we'll talk a bit about how this was discovered. I think a lot of you heard that recently, and this is an artist's conception, of the first confirmed interstellar asteroid, something that actually whipped by our solar system this fall. It was discovered October 19th of this year by the Pan-STARRS 1 telescope in Hawaii. And this is an object that was named Oumuamua. And that's a Hawaiian word in honor of its discovery in Hawaii. And it translates roughly into visitor from afar who arrives first. It's the first time we've actually confirmed something came from outside our solar system. So how do we know that? Well, a lot of people know that most of the asteroids are in the plane of our solar system. You know, we see them along the ecliptic. There is also the Oort cloud of comets, which is a spherical distribution of comets all the way around the solar system out to a distance of about 2 light years. So when I first heard about this, they said, well, it's coming in, way perpendicular to the ecliptic. I said, well, that's nothing special. We see comets doing that all the time. But the thing that was amazing about Oumuamua was the speed it was coming. So this thing came into our solar system at about 60,000 miles an hour. And when it whipped around the sun, it actually was going as fast as 196,000 miles an hour. That is easily escape velocity from our solar system. This thing is going way too fast to have ever been bounded by the sun's gravity. It came from the direction of the star Vega in the sky, but we don't think that that's necessarily from Vega. This thing has probably been in interstellar space for millions or even billions of years. So Vega wasn't in that direction when it began its journey, and now it's heading off in the direction of the constellation Pegasus. It'll never return to our solar system again. Now, the artist's conception is based on actual observations of this. Once we discovered this, pretty much every asset that NASA had, a lot of our space-based telescopes, as well as our ground-based telescopes, observed this thing. It's about half a kilometer across, about 5 football fields in length. And the thing changes in brightness so much that it tumbles about once every 7 hours. And as it does, that led us to estimate that it's about 10 times longer than it is wide. And that is entirely different than any other asteroid in our solar system. The largest aspect ratios we get in our solar system is 3-to-1. So this is like a little shard. People have called it cigar-shaped. And it has to be pretty rigid because it's actually tumbling that fast, about once every 7 hours. It's reddened, a lot like other outer solar system objects that have been in radiation for a long time. And it's not giving off any type of volatiles. So when we saw this thing coming in, we were thinking it might be a comet, that we thought that'd be more likely than an asteroid. It's not giving off any sorts of gases. It's rocky and hard, and off it goes. So there's Oumuamua. How do you find an object like this? If I could have the next slide. In 2005, NASA was tasked by the U.S. government and part of our legislation to actually find 90% of the asteroids out there up to a distance of about 140 meters across. These are the ones that we think are dangerous to the Earth. 140 meters across is not anything like a dinosaur event, but that would take out a city. So that's something that you really, really want to be very careful about. Now, this is an animation of all of the discoveries of asteroids. And if you look at the date down here, that's at the bottom, it starts in 1980. And what you'll see as this sort of continues is that the asteroids light up as little blue dots as they're discovered. And then they sort of fade into green dots, so you can just see how many there are. So you're looking down on a schematic of our solar system. You've got the sun in the middle, got the orbits of Mercury, Venus, Earth, and Mars, and so on. So these are asteroids that you'll see a lot of them actually crossing in towards the Earth's orbit. As most people know, the majority of asteroids are located between the orbits of Mars and Jupiter, and you see them out here. But the thing that's kind of interesting to me as this goes on is NASA has a lot of work to do to actually find all of these asteroids down to that size. We think we've identified over 90% of the ones that are seriously risky ones, ones that are actually sort of global impact. But as far as these ones that are 140 meters, we think we've actually identified about a third of them. We've found about 8,000 of them since the time that NASA was asked to do this, but estimates put them around 25,000 total. So we've got about 2/3 left to go. So that's one of the things that we're doing. NASA has a network of both ground-based telescopes and also space-based telescopes that are looking for these. I think that animation is actually running a little slowly, so let's go on. Okay, now, what people know about asteroids, of course, they're rocks. They tend to be leftovers from the beginning of the solar system, so they're very scientifically interesting. These things haven't been modified for billions of years, we think. Some of them are very large. There's some that actually qualify as minor planets, like Ceres. Ceres is actually a dwarf planet. It's about 800 miles across. This is a picture from the Dawn mission of Vesta, which is about 300 miles across. That's a very, very big asteroid. A lot more of them are smaller, as we mentioned. Here's one that's only about 1,800 feet across. But Itokawa is also interesting because it shows you how different asteroids can be. Asteroids don't have to be just one big solid rock. They can kind of be floating junkyards. And this is actually what we think of in the case of Itokawa, that these are all kinds of small rocks and dust conglomerated together due to gravity. And this changes your strategy as to how you try to mitigate asteroids. Because, people talk about, the movie version, you send Bruce Willis with a nuclear bomb, you blow it up. Something like this, which isn't really a solid body, it's just lots of things kind of conglomerated together under gravity. Basically, if you throw a nuclear bomb at that, you just make it mad, you just heat it up. So that doesn't change it much. So there's a lot of strategies we need to think about how to really mitigate these things properly. So next one. Yeah, this is just to kind of remind you. As we said, the scale of asteroids we're looking for, things that are about 140 meters across, something like that could create something on the order of meteor crater. We also have larger meteors in existence, like this one in Quebec that's 62 miles across. The Earth has erased most of the asteroid impacts pretty efficiently, but we know that these are going to happen. And as Randy just said, in the case of Shoemaker-Levy 9, that thing would have resurfaced the Earth. So this is something we need to at least have a strategy to deal with. Next slide. Okay, in comes NASA's Planetary Defense Coordination Office. So we actually have an office that works with other agencies like FEMA to prepare for natural disasters like this if they ever happen. And as I mentioned, we're now tasked to find 90% of the dangerous asteroids, and we're working on that right now. Next slide. So the goals is we need to first detect these things, find out where they are and whether they're hazardous. And we have a combination of space-based telescopes and ground-based telescopes. This is the WISE mission, which was the Wide Field Infrared Survey Explorer mission. And this was actually an astrophysics mission that was launched to study the infrared sky. But when its coolant ran out and the detectors became warmer, it wasn't sensitive enough to do a lot of the astrophysics, but it was still sensitive enough to detect asteroids. Asteroids emit a lot of the infrared, and so WISE was retasked to become NEO-WISE, the Near-Earth Object version of that mission. So it scans the skies looking for these asteroids. And then we also have a system of ground-based telescopes that include the Pan-STARRS telescope in Hawaii, but also Linear and the Catalina Sky Survey. So these are all over the country and the world scanning the sky continuously for detecting these asteroids. Next slide. We also have radar assets. This is the Goldstone Radar dish and also Arecibo in Puerto Rico. And when these asteroids are detected, when they get fairly near the Earth, we're able to bounce radar off them and take pretty good images of what the shape of them is. This helps us with the composition as well. So those are sort of two prongs of the way that we detect the asteroids and characterize them. And this is all funded by NASA. Arecibo, of course, took a big hit during Hurricane Maria, but we're getting that up and running again. Next slide. The unfortunate thing about the timing with Oumuamua, the interstellar asteroid, is that the Arecibo Telescope was down after Hurricane Maria, so we never actually got any radar measurements of that. Okay, now, as I mentioned before, how do you actually really mitigate an asteroid threat? We, just being physicists, did a calculation. In Bruce Willis's movie Armageddon, the asteroid was the size of Texas, and they blew it up right as it was entering the atmosphere to split it in two and have it avoid the Earth. And I think we calculated that you'd need the energy output of the sun for that to happen. So that's not how we're going to do it. So let's try another one. Next slide. The main thing you want to do is detect these things as long out as you possibly can. So the sooner you get them, the more time you have to go out there and find a way to change their orbit, even just a little bit. If I could have the next one. The whole point is find it far away, years before an impact happens. Find some way to correct its course just a little bit. Shove it, kick it, hit it, drag it. Don't try to destroy it. You don't want millions of things on the same path of that asteroid coming at the Earth that might actually be more dangerous than a single object. And the whole idea is change it just a little bit. Speed it up years in advance, just a couple centimeters per second, or slow it down, same amount, and have it arrive at the orbit it would have been, but just 20 minutes late. Have it just miss the Earth. That's the goal. Next one. So NASA is actually working on this. We're actually coming up with different strategies about how you would actually do this. So if I could have the next slide, there are a couple different ways you would do this. One thing that we're actually developing right now is something called the DART mission. And the DART mission stands for the Double Asteroid Redirect Test mission. And the idea is it's going to fly out to a double asteroid called Didymos, and this is now in development. Didymos is a near-Earth asteroid, and it's actually a binary asteroid. The main body of the asteroid is about 800 meters across, and that's pretty big. But it has kind of a moon. It's a binary, but one of them is quite a bit smaller than the main body. And the moon of Didymos is about 150 meters across. So this is the scale of things that we really want to be able to influence. And the idea is actually brutal but effective. We're going to take this spacecraft and just plow it into this small asteroid and see how much we can modify the course of that test, how we can speed it up or slow it down just based on that impact. So we are actually designing something to go out right now and actually smack an asteroid. You don't have a lot of control when that happens. You don't know exactly how much you're going to be diverting it. So the other thing to do is something called a gravity tractor, where you fly along an asteroid you fly a spacecraft alongside an asteroid and just let the gravity of that spacecraft, that tiny little tug, just slow it down or speed it up a tiny amount. And that's another thing that they're looking at. Next slide. Now, there's a lot of things that we need to discover about asteroids before we get really good at being able to redirect them. And so last year we launched, it was actually in 2016, we launched the Osiris Rex mission. And this acronym is one of the banes of my existence. Let's see if I can do this. It's the Origin Spectral Interpretation Resource Identification Security Regolith Explorer. Yeah, all right. Yes, okay, there we go. Osiris Rex is an absolutely amazing mission. It successfully launched in 2016. It's currently on its way to a half-a-kilometer-sized asteroid called Bennu. And it's going to be mapping and orbiting Bennu for a couple of years. It arrives this August. So stay tuned. This August 2018, we're going to be arriving at Bennu. And then the really cool thing is that in order to better understand how asteroids work, it's going to be collecting a sample of the asteroid material and returning it back to Earth. Next slide. One of the main goals, here's a picture of the spacecraft, relatively small spacecraft. You can see the solar panels, but you can also see this capsule up here. And there's a robotic arm, I'll show you an animation of it after this, that's going to come out and actually sort of vacuum up some of the particles from the surface of the asteroid and deposit it in this canister. And then this canister will return to Earth in 2023. So, I mean, that'll be tremendously exciting. In a couple of years, we're going to have a big, pristine sample. We hope at least a kilogram. Yeah, I think the goal is 60 grams, but they're hoping for up to a kilogram or maybe 2 of material. Next slide. Now, one of the things that we really need to understand first before we get good at diverting asteroids is something called the Yarkovsky Effect. And asteroids' orbits actually change based on how they absorb and emit sunlight. So you have sunlight warming up asteroids, and it's not warming up the whole surface evenly. These things are very irregular. They may be irregularly colored. They may have different consistencies. And so as sunlight warms up the asteroid, as the asteroid radiates that heat into space later on, it's almost like a very, very weak jet engine. And that changes the path of the asteroids. So when people say, do we know of any dangerous asteroid impacts coming up? Well, the answer is no. In the next 100 years, we know of no big dangerous impacts coming up, but we also know that asteroids change their paths based on this effect. So one of the things that Osiris Rex is tasked with doing is it's going to be in orbit around this asteroid for the better part of 4 years, and it's going to be studying exactly how this Yarkovsky effect works. Next slide. And then just to wrap up, this is sort of an animation of what's going to be happening. So, starting in about 2 years from the summer, it's going to map the asteroid for a couple of years. It's going to identify the best place to take a sample. And then it's going to not really land, but actually fly up alongside the asteroid. We sort of call it a high five, and just touch the surface of the asteroid, put that stuff back in the canister. It's going to do a lot of mapping and studying the asteroid in general, but then it comes back, and in 2023, we get our canister full of asteroid material. One of the things that I find kind of wonderful and inspiring is that 75% of that sample will actually be put away. We're not even going to look at it because we are sure that in generations to come, in decades to come, we're going to have better instruments to analyze that. And this is one of the things that happens in archaeology these days, that when you discover something really interesting, you cache it, you put it away. You don't even look at it because in generations to come, there's going to be better material for actually better instruments for analyzing that. So this is one of the parts of NASA that I think people aren't really aware of. We are scanning the sky continuously every night for any sort of dangerous asteroids. We are trying to make a census of them, figure out how to mitigate them, but also do the original science, because asteroids are fascinating. And as Oumuamua now leaves our solar system, it's going to be out around the orbit of Jupiter sometime next year. It's going really, really fast. It's cruising speed through the stars. So it came and accelerated around the sun, and then it'll decelerate as it goes back out. But it's going to be going about 60,000 miles an hour. That covers 1 light year in about 11,000 years. So we don't know where this thing is going. We don't know where it came from. It was found using our Planetary Defense network. So stay tuned, and also stay tuned for wonderful missions like the Osiris Rex. Thank you.